Thank you. Hi everyone, my name is Patrick, like he introduced me. Yeah, I've been working at the Technical University of Munich since 2017, and since 2020 we've actually been printing with one of CEAD's flex spots. And at the Technical University we're part of the Department of Aerospace and Geodesy, which means that most of our work is for some kind of aerospace application. And at the chair, we mostly look at the three topics: material behavior, process technology, and modeling and simulation. And the project that I want to talk about right now focuses on all three of them. But for this presentation, I'll focus on the material behavior and the steps that we took to find a PAEK which works well when printing very big parts in a cold, unheated environment. So I want to talk about a Clean Sky 2 project in which we printed a resin transfer mold for Saab to produce a flap run for an Airbus A350. So the part you see in the picture is about 3.10 meters in length, and it has to withstand quite tough process conditions. So you inject resin into it at 8 bars pressure. You then cure the whole thing at 180 degrees Celsius. It's quite long, and the part you produce with it is actually hollow. It's a wind structure, and the thinnest part is in the middle, so you need cores going into the part from both sides. And the part you manufacture is a carbon composite shell, which itself has a very low CTE, so a requirement for us was to try and match this CTE as closely as possible. Overall, the objectives as to why we would want to try and print a mold of this size was to decrease the lead time of these molds. They are usually milled from either aluminum or Invar, depending on whether it's a prototype tool or serial production tool. We actually also wanted to have shorter cycle times in composite production, and we wanted to achieve this by heating up and cooling down quicker by integrating cooling channels just below the surface of the mold. And a thing that Saab was quite adamant about is that they wanted it to have a lifespan as long as possible, so they wouldn't have to replace it all that often. Like I said, we were planning to print this in PEEK, and most of you probably know PEEK is not a cheap material. So the idea was, if we have to replace it, it should be easy and cheap to repair. And another kind of difficult requirement, but where 3D printing really helped us, was they wanted to achieve the same quality in RTM process as they do in prepreg, which is already kind of difficult in metallic tooling, but it's especially difficult for a part as complex as this, where you have several colliding flow fronts. And yeah, the way we approached these challenges, first the CTE, was we printed it in a way that all the fibers align along the long axis of the print. So we actually printed it standing up and had very long extrusion lines, which in turn also meant that we have very long layer times and the material cools down quite far, which can be difficult for PEEK as it tends to delaminate, but BigFlex found a solution for that. Yeah, the internal heating elements meant we had a lot of start and stop. We had travel moves in between individual print segments, where the melt pump from CEAD really helped us get that printed without oozing everywhere. And yeah, the long lifespan in direct contact with the resin is actually why we chose PEEK. So many of you probably are thinking that you could print this with PEI and it's easier than PEEK. And it's probably right. The problem is that PEI is actually soluble in the resin that you use for RTM in aerospace industry. So if you have direct contact with the resin, your part will permanently become part of your mold, which means you'll have to replace it quite often. And for the injection problem I mentioned before, you can actually see in the picture, we have these, oh, you actually can't see my mouse. You have these connections here. So the cores are actually hollow, And you can push the injection lines all the way through the cores to the dotted line, and then you fill the part from the inside out, something that's not possible with metallic tooling, where you have the parts machined from a block. First of all, because the cores are about 1.5 meters in length, and second of all, they're slightly curved. Yeah. So why did we choose PAEK? Like I said before, we have high curing temperatures of 180 degrees, and PEEK is form stable until 240. And the most important two parts are the superior chemical resistance. Since it's semi-crystalline, it doesn't dissolve in the resin, it is resistant to most solvents, and it has a very good wear resistance. So if you demold your part quite often, you don't damage your tool surface as quick as you would with an amorphous polymer. But probably all of you know the pyramid. The further up you go in the pyramid, the higher temperature resistance you get, the better material performance you get, the more expensive it gets, and the trickier it gets to print it. So since we chose something that's pretty far up at the top, we had to make sure that within these polymers we choose one that's relatively easy to print for a PAEK. And there's a couple of considerations that we took. The first one is we were going to have very long layer times, and we somehow needed to reduce them. So to maximize our output, we started looking at the viscosity of the polymers. And yeah, in 3D printing, the shear rates are actually quite low. So you're usually somewhere on this end of the diagram. In injection molding, you're usually somewhere on that end of the diagram. And if you get a viscosity indication on a data sheet, quite often it's one that you have somewhere over here. And polymers that behave very similarly in injection molding might behave very differently in 3D printing. So we ended up choosing one with a viscosity as low as possible and a crystallization speed as slow as possible. So in our case, it's the blue line. Which brings me to my next point, the crystallization speed. Once we've maximized the output and we can print as fast as we can, the other trick is to just increase the time that we have, that the polymer needs before it's not bondable anymore. And Victrix actually has a couple of different PAEKs in their portfolio which crystallize at different speeds. This is from one of the earlier material trials when we were still using filaments, but it shows my point quite nicely. They're all manufactured the same way, and the one on the left is almost fully transparent, while the one on the right is completely opaque. And it just shows you how differently they crystallize. The opaque one is fully crystalline, and the transparent one is amorphous. And you can also see it in the DSC diagrams, that the peak not only moves to lower temperatures, but it also becomes wider, which means the crystallization happens slower. And we ended up going for the slowest crystallizing one. I don't think that one's been commercialized yet. The middle one is now known as AM200, if I'm right. We opted for the even slower crystallizing one because you can actually completely suppress crystallization in 3D printing. So with this polymer, so it's a DSC graph, and the little peak you see here is when the crystallization happens. And the more crystalline your material is, the less you see of the glass transition temperature. And basically what you can see here is that anything that's cooled quicker than 25 kelvins per minute doesn't crystallize at all, which is a speed that you can quite easily hit in 3D printing, even with the large systems. And what will happen is that once the layer is deposited, it will cool down quickly, and the surfaces will stay amorphous and bondable. And when the next layer is deposited on top, you again apply heat. You can still bond the layers together, and then the residual heat will crystallize the layer below. That's the idea behind it. So hopefully, if everything works, it should make the PAEK behave more like a polycarbonate, which also has a glass transition temperature at about 150 degrees Celsius, like this PAEK. So that was to help us with layer bonding. I'll have some strength values for you later on. Next issue we have at the 3-meter part, apart from layer time, is warping. So we had to look at minimizing the CTE, and an easy way to minimize the CTE is by just adding carbon fiber. The carbon fiber basically blocks the polymer from shrinking. So by adding more and more carbon fiber in your polymer, you can reduce the CTE quite drastically. And the picture on the left actually shows you how the CTE drops by adding more carbon fiber, and the one on the right is again the viscosity by adding more carbon fiber. And what's interesting to see is that by adding a little bit of carbon fiber, your viscosity drastically increases. But if you add more carbon fiber, the following increase is really not that high. So if you're going to add carbon fiber, you might as well go for it and add a lot of it, which will help you with the CTE and really push it down. We ended up going for one with 30% carbon fiber. And with those polymers, I ended up doing a couple of tests, printing cubes at different speeds and sizes to get different temperatures. And I actually printed one cube. I printed a couple more cubes with a standard PAEK from injection molding. It's the little orange dot at the bottom. And with injection molding PAEK, the bonding you get is actually so bad that most samples break during preparation, which is why we only have one spot down there. But with these slow crystallizing polymers, you get, first of all, much higher strength at the same substrate temperature, but you also achieve better bonding at much lower substrate temperatures. So substrate temperature for me is how is the temperature of the layer just before the next layer is deposited on top. And you can actually see that even below 150 degrees Celsius, which is below the glass transition temperature for the substrate, you still get bonding which is much better than it would be for injection molded PAEK at over 200 degrees Celsius. So to conclude this a little bit, selecting the right material is a very important aspect of successfully printing a large 3D printed part. The two other really important aspects, in my opinion, are the machine, which you can get a pretty good one back there, and the application design. So how you design your part, how you do the tool planning and everything also has a huge impact on the success of your 3D print. And yeah, the big benefit of this slow crystallizing PAEK is that it kind of combines the best of both worlds. In the finished product, you'll have the high chemical resistance of a PAEK because it's crystalline, but during processing it behaves like an amorphous polymer with good bonding and actually also a little less warping. Yeah, that's actually also it content-wise from my side. A few colleagues of mine are here today. Like I said on one of my first slides, TUM is actually a huge university with 10,000 employees. So we actually do a little bit more than just aerospace. Pretty much everything from metal to ceramics and concrete. And they're actually here today as well, if you want to visit them. And if you have any follow-up questions, you can contact either me, though I'm not really that much involved in the activities at the chair anymore, or you can contact my colleague Matthias. He actually also worked on this project, and he's actually still working on the seat flex spot at the chair in another aerospace project also for tooling. So yeah, that's it from my side already. Thank you.